Cement is much more than just a material. It's the glue of modern civilization. It's found everywhere, in roads, bridges, skyscrapers, tunnels, dams, and even in the humblest homes. It's used to bind bricks, stones, and blocks together, forming the basis of mortar and concrete, the latter being, after water, the most widely used substance on Earth. In this video, we'll delve into the fascinating process of cement manufacturing, from open-pit quarrying to bagging the finished product, exploring the invisible chemistry hidden within giant kilns. We'll also discover its millennia-long history and the revolution it sparked in the construction industry. Before we begin, don't forget to like, subscribe, and turn on notifications so you don't miss any of our documentaries. The idea of a mineral binder is not new. The first civilizations, more than 5,000 years ago, already used rudimentary mixtures capable of solidifying structures. The Egyptians, for example, combined clay, straw, and gypsum to create sun-dried bricks, which were used to build their homes and temples. But it was the Romans who perfected this art. Between 200 BC and 100 AD, they mixed lime with volcanic ash and fine sand. This mixture formed an impressively strong binder called opus caementicium, from which the word cement comes. The structures they left behind, such as the Pantheon in Rome and the aqueducts of Segovia, still stand today, a testament to the effectiveness of their technology. Their monumental domes and vaults still rest on this cutting-edge engineering material. However, it wasn't until 1824 that modern cement was born, when an English mason, Joseph Aston, patented Portland cement. Its name comes from the resemblance between the color of hardened cement and that of Portland stone, quarried on the south coast of England. This marked the beginning of a new era for architecture and industry. All cement begins its life in rock. The main ingredients, limestone, clay, sand, and iron ore, come from massive quarries, often located in the immediate vicinity of the plant. The choice of site is strategic. It must minimize transportation, since every ton of material moved costs time, fuel, and energy. The extraction begins with a spectacular scene, a controlled detonation, drills piercing the ground to a depth of several meters. The holes are then filled with ammonium nitrate-based explosives, carefully measured to fracture the rock without pulverizing it. The entire assembly is connected by a network of cables to the main detonator. A few seconds after ignition, the mountain rumbles. The ground trembles. A perfectly calculated explosion releases up to 200,000 tons of limestone in a single blast. The blasted blocks are immediately loaded into gigantic mining trucks, each with a capacity of approximately 60 tons. Hydraulic excavators equipped with 12 cubic meter buckets can lift up to 17 tons of stone with each movement. These rocks, destined to become the base for cement, then begin their long journey to the factory. The first industrial step consists of reducing the size of these blocks of rock. The trucks dump them into a primary crusher, a massive machine equipped with hardened steel hammers or jaws. Under impact, the blocks break down into pieces the size of a tennis ball. This operation, called primary crushing, facilitates handling and homogenizes the material. The stone fragments are then transported by conveyor belts to the storage area, where they are stacked in alternating layers in a prehomogenization process. The aim is to standardize the chemical composition of the materials from different quarry faces. Then comes the dosing. Automated systems, controlled by the central laboratory, precisely weigh and mix limestone, clay, iron ore, and sand according to the chemical recipe of the desired cement. This calibrated mixture is sent to a roller mill or ball mill, where it is finely pulverized into an extremely fine gray powder called raw meal. This raw meal has a carefully balanced chemical composition. It consists of approximately 75% calcium carbonate, 20% silica, and small amounts of alumina and iron oxide. Once crushed, it is sent to large homogenization silos, where powerful air currents continuously agitate it to ensure perfect uniformity. This is where the magic of chemistry happens. The raw flour enters the preheating tower, an imposing structure several tens of meters high, equipped with successive cyclones. As it descends from cyclone to cyclone, it is swept by a current of hot air rising from the rotary kiln. In a few seconds, its temperature rises from ambient temperature to 850 degrees Celsius. At this stage, the flour undergoes calcination. The calcium carbonate decomposes, releasing carbon dioxide and transforming into calcium oxide, also known as whey. This chemical phenomenon marks the beginning of the mineral's transformation. The prepared material is then introduced into the rotary kiln, an immense inclined cylindrical chamber over 60 meters long, which rotates slowly on its axis. Inside, the temperature reaches 1,450 degrees Celsius, enough to partially melt the rock. It is there, in this incandescent cylinder, that clinker is formed, a lumpy material composed of hard, dense, spherical gray nodules. Clinker was the heart of cement. It was clinker that, once crushed and mixed with gypsum, gave the material its ability to harden on contact with water. To guarantee its quality, the kiln operates continuously, 24 hours a day, all year round, because a single stoppage would cause the kiln to cool down and the material inside to solidify. When the clinker leaves the kiln, it is still at 1,000 degrees Celsius. It then passes through a grid cooler, where a powerful blast of air lowers its temperature to approximately 100 degrees Celsius. The speed of this cooling is crucial. If it's too slow, the crystals won't form properly, reducing the mechanical strength of the future cement. Once cooled, the clinker is conveyed to ball mills, where it is ground into powder again. But this time, small amounts of gypsum, about 5%, are added to control the cement's setting time. Without this regulator, the cement would harden almost instantly upon contact with water. Depending on the desired type of cement, other additives can also be incorporated. Blast furnace slag, natural pozzolan, or fly ash from thermal power plants. The crusher, a steel cylinder filled with thousands of metal balls, rotates on its axis. With each rotation, the balls cascade down onto the material, crushing it by impact and abrasion. Gradually, the clinker and additives become a homogeneous and extremely fine powder, cement as we know it. Throughout the process, samples are taken for analysis. In the laboratories, spectrometers verify the chemical composition, while mechanical tests measure compressive strength. The fineness of the grind, the proportion of fine particles, and the curing time are also rigorously controlled. Once approved, the cement is stored in large metal silos before being sent to the bagging line. High-speed automatic bagging machines fill multi-layered craft paper bags, which are tear-resistant and moisture-proof. Each bag contains 50 kilograms of cement, weighed with millimeter precision by electronic scales. The bags are then stacked on pallets and wrapped for transport. Cement can also be delivered in bulk in tanker trucks, destined for concrete plants and large construction sites. Today, cement is at the heart of the modern world. Every year, humanity produces more than 4 billion tons of it, or more than half a ton per person on Earth. From Dubai's skyscrapers to China's suspension bridge, from American highways to African dams, cement shapes our everyday environment. But its energy-intensive and CO2-emitting production also raises new challenges. Increasingly, factories are innovating by integrating renewable energy, more efficient kilns, and green cements with a reduced carbon footprint. Thus concludes the long journey of cement, an adventure where stone becomes powder, where chemistry meets engineering, and where humanity transforms raw materials into sustainable architecture. Behind every building, every bridge, every house lies this gray dust born of fire, time, and human know-how. If you enjoyed this documentary, please like, subscribe, and turn on notifications so you don't miss any of our content. But don't go away just yet, there's more. The rest of this video will be just as exciting, so stay with us until the end.
The world's largest source of recycled steel doesn't come from mines. Guess where it comes from? The automotive recycling industry, often called the second life of cars, which supplies the global market with a colossal flow of steel each year. In the United States alone, more than 12 million vehicles are dismantled and recycled annually, transforming car huts into veritable artificial steel mines, among the most efficient ever created by humanity. Every car we thought was reaching the end of its life is actually beginning a new journey. In this video, we'll see how used vehicles are transformed into raw materials, ready to build infrastructure, fuel industry, and even give birth to the next generation of automobiles. You buy a car for $48,000. After 10 years on the road, what value does it retain when it enters the recycling process? Behind this question lies a $60 billion a year industry, where millions of vehicles are dismantled, crushed, and reborn as new raw materials. This cycle provides hundreds of thousands of jobs, significantly reduces the costs associated with metal smelting, and significantly reduces the environmental burden. And if iron ore represents a natural mine, then end-of-life cars are a limitless artificial mine. Each recycling cycle saves up to 74% energy compared to extracting new ores. On average, 75% of a vehicle's weight can be recovered, from steel to aluminum, including glass and plastics. As a result, each year, hundreds of millions of tons of materials are reborn and continue their journey in the form of buildings, everyday products, and even new cars. When a car reaches the end of its life, it is taken to the receiving area of a recycling plant. There, technicians record its vehicle identification number, engine number, year of manufacture, general condition, and all associated documents. They photograph it, assign it a tracking code, and integrate all the data into a digital management system. This step not only guarantees full traceability of the process, but also allows for the residual value of each vehicle to be assessed. The inspection focuses on reusable components, such as the engine, gearbox, electronics, and interior parts. These usable items are isolated and feed the multi-billion-dollar used parts market. Vehicles that are too damaged or completely worn out, on the other hand, are sent directly to disassembly for material recovery. Once this step is complete, the vehicles are organized into batches in the yard, lined up, and ready to enter the processing line in a clear and systematic manner. Few people know this, but in the United States, more than 95% of end-of-life vehicles pass through this system, making cars the most recycled consumer product in the world. Thanks to this level of organization, each vehicle maximizes its recoverable value and contributes to the economy. Once the inspection is complete, the vehicle enters the processing area. The first step is to remove the battery, the main electrical hazard still present. In combustion engine cars, the lead-acid battery is removed immediately. This type achieves a recycling rate of over 98%, as the lead, plastic, and even sulfuric acid can be reused to make new batteries. For hybrid and electric vehicles, the much larger lithium-ion battery packs require an even more stringent procedure. They are carefully detached, securely packaged, and shipped to specialized centers. Only after the complete electrical system has been removed can a vehicle be further dismantled. After this step, the car is placed on a platform to extract fluids: gasoline, engine oil, transmission fluid, brake fluid, coolant, and even air conditioning refrigerant. Hydraulic clamps secure the chassis, while a steel probe pierces the tank and sucks out the fluids using a high-pressure water vacuum pump. On average, a decommissioned vehicle still contains several gallons of fuel and fluid, enough to cause fire, explosion, or pollution if not handled properly. Within minutes, everything is drained and directed to underground tanks. A notable feature is that nothing is wasted. After filtration, the majority of the recovered fluids are reused to power the plant's forklifts, generators, and other machinery. The remainder is stored for internal needs, significantly reducing energy costs. Throughout this process, pressure sensors, check valves, and sealing plugs ensure a completely closed system, preventing vapors from escaping and ensuring the safety of the line. Once the fluids have been extracted, disassembly of the main components begins. Wheels are usually removed first because they take up a lot of space and are easy to process. Used tires are among the most difficult waste materials to decompose, requiring decades of disposal in landfills. Instead, most are ground into rubber granules for asphalt pavers or playground equipment, while others are used as alternative fuel in industrial furnaces. Steel or aluminum rims are sent directly to the foundry for recycling. Next come the windshields and windows, cut using specialized tools. These laminated glasses, reinforced with a layer of PVB, prevent shattering. Recycling allows for the recovery of glass, but also PVB, which is reused in soundproofing materials and industrial coatings. Next, the doors are dismantled, a seemingly simple element, but made of multiple materials. The steel or aluminum frames are cut to be remelted, while the electric window motors, locking system, and wiring are separated to extract the copper, plastic, and magnet. The interior follows: seats, dashboard, and carpeting. Everything is carefully disassembled and sorted. The cables are stripped to recover the copper, while the plastic and textiles are shredded and transformed into new materials. Finally, the engine and transmission, the heaviest and most valuable mechanical assemblies, are removed. Some are refurbished for resale, others disassembled to extract aluminum, steel, copper, and even precious metals from the catalytic converters. This methodical sequence maximizes the value of each part and prepares for the next step, crushing the car's body. Before entering the press, the car still retains various non-metallic components that are difficult to process, such as twisted exhausts, large plastic panels, and tangled cables. These residues are removed in a pre-treatment area where immense mechanical arms equipped with hydraulic shears come into action. With forces of several tens of tons, these steel jaws tear off the remaining doors, extract exhausts, or reduce radiators in a few seconds. Plastics, foams, and non-meltable materials are immediately discarded. With this raw power, the chassis is quickly cleaned, much faster than by hand. This step acts as a coarse filter, removing materials that could ignite, contaminate the recycled metal, or damage the press. In just a few minutes, the structure is reduced to a clean steel and aluminum shell, ready for compaction. It is then introduced into a massive hydraulic press. Under a crushing force of 150 to 200 tons, a structure of more than 4 meters is compressed into a compact block. Its volume is reduced to 1/10 of the original. Depending on the technology, this process is carried out using different machines. The baler transforms the chassis into a dense, stackable cube that is easy to store and transport. Modern balers can process 25 to 40 vehicles per hour, making them ideal for large sites. The flatbed compressor is preferred for medium or small vehicles. It flattens vehicles into sheets a few dozen centimeters thick. Faster and less energy intensive, it nevertheless offers a lower density, making subsequent crushing more energy intensive. As for the shear baler, it compresses and cuts the vehicle into sections ready for crushing or even direct casting. Different methods, but the same goal: transforming a bulky carcass into uniform metal, ready for a new life. Once compacted, the dense steel bales are fed into a high-capacity industrial crusher, the true heart of the line. Inside, massive steel shafts with interlocking teeth rotate in opposite directions, tearing the block apart in seconds. The metallic crash amplifies the air, and in an instant, a car occupying an entire space is reduced to homogeneous steel fragments. The pace is dizzying. A modern shredder can process 100 to 150 tons of steel per hour, or several hundred vehicles per day. This efficiency allows the automotive recycling industry to operate on a large scale, transforming mountains of scrap into raw material ready for melting. After shredding, the mixture of metals and non-metals moves along a sorting line, using powerful magnets for steel and eddy currents for aluminum and copper. Plastic, rubber, and textiles are disposed of. Recovered steel is compacted into bales for the foundry, while aluminum and copper are separated for other industries. In less than an hour, an abandoned car yields pure, reusable metals, ready to re-enter the production cycle. What was once just a carcass is now compacted, crushed, sorted, and grouped into standardized bales. The recycling journey thus enters a new phase. These blocks are sent to an electric arc furnace. There, they face infernal heat. Graphite electrodes release currents of tens of thousands of amperes, generating an arc similar to artificial lightning. Within minutes, the temperature climbs to over 1,600 degrees Celsius, transforming the steel into melted steel. Hot and molten, they absorb impurities, forming a layer of slag, while jets of oxygen burn away unwanted elements. Sensors and spectrographic analyses continuously monitor the composition to ensure a perfect alloy. From a chaotic heap of worn parts, now emerges a glowing sea of pure steel, ready to be cast into semi-finished products. The refined liquid steel is immediately conveyed to the continuous casting line. A glowing stream flows into water-cooled molds, solidifying on the surface in seconds, while the core remains liquid. Rollers guide the slabs and billets along the line, where they gradually cool. This creates long square bars for construction or flat plates that will be rolled into sheets or coils. Automated thermal saws cut them into standard segments weighing several tons. Each piece is numbered, scanned, and recorded as a batch. From a stocking to a metal form, S-shaped blocks become standardized, opening a new chapter in the cycle. As they leave the reheating furnace, the glowing billets enter the hot rolling mill. There, huge rollers press, stretch, and bend them into uniform sheets or coiled. With each pass, the metal flattens and elongates, evolving from a rough block into regular sheets. Ultra-fast cameras and laser sensors measure every millisecond, monitoring thickness and straightness to ensure perfect precision. This work is reminiscent of a metal sculpture, both powerful and extremely precise. Rolled steel cannot be shipped immediately. It must be cooled in a controlled manner. High-pressure nozzles cover it with a white mist, rapidly lowering the temperature without cracking. Then, powerful fans ensure gradual cooling that preserves its internal structure. Once at a safe temperature, each coil is inspected. An ultrasonic sensor detects hidden cracks, a high-resolution camera analyzes the surface, and a mechanical test measures strength. Only those that pass muster are marked and stored. From its incandescent glow to its masterful strength, steel is ready to serve hundreds of modern industries. Thus, from a seemingly useless old car, recycling opens up a whole new life. It all begins with careful disassembly, safe emptying, and then crushing under hundreds of tons of pressure, followed by the roar of the crusher. The metals are then precisely sorted before being melted down to become new steel. Rolled, cooled, and inspected, the latter becomes a durable and clean material, ready to support construction, industry, and the manufacture of new automobiles. Every end-of-life vehicle, far from being waste, fuels a multi-billion-dollar industry, reduces energy consumption, and relieves natural resources. Recycling is not only an ecological solution, it's also an invisible pillar of the modern economy. Have you ever considered that the car you drive today could one day become the steel of a building, a bridge, or even another car? Share your thoughts in the comments, and most importantly, don't forget to like, subscribe, and hit the bell so you don't miss any of our upcoming content.